welcome back. Shall we restart? So, need your help again with yeah, this
and the last one.
Thank you. Right. So during the break, most of the questions were related to logic tensor networks, and some were more generic. So I'll try to spend most of the time there looking at LTNs, but I really want to just spend some time on the SIL++ system, because it is entirely inspired by inductive logic programming, and so I assume related to this summer school quite closely. So I will have to jump through some of the slides, but hopefully you will find those slides useful at a later time. Just to give you the general idea of the system, and I don't need to motivate relational learning in this community, but just to point out that whenever we do these things, we should, whenever we propose to use neural nets in the context of relational learning, then we need to compare results with probabilistic ILP approaches, MLNs, for instance, blog, and star AI lifted inference proposals. And you'll see when I show the tables that I didn't do that. So I'm hoping that others will take that task. But we did compare with Aleph, and we have some interesting results there. So I mentioned already Pozmolensky's seminal paper, and there are many early attempts to represent first-order logic in neural nets, either for the purpose of performing reasoning with neural nets, or to try and learn those representations. And I'm just listing some here. Hitzler, the team at Osnabrück, the Shruti method, and many other attempts that were kind of left out there. And when we picked this up, we had to take a more practical approach. And by that, what we mean is that we took a propositionalization approach. So you could try and perform inductive logic programming at the level of first-order hypothesis search, but it seems to me that when it comes to trying and doing it in a neural net, one would need to take this, or the most natural choice would be to take a propositionalization approach. And this is somewhat similar to the QGGA approach of Muggleton et al., where you would replace your genetic algorithm, in that case, by a neural net trained with backpropagation. So the system is based on what I've shown you, but it has these three steps. We propositionalize bottom clauses. We apply a neural net for learning on those vectors with backpropagation and early stopping. And then we present the result in first-order logic representations following learning. And what these results indicate is that such approach can achieve comparable accuracy while being considerably faster, and with early stopping, we can get some compact representations in comparison with other ILP systems. So, just to mention that as we go through this process of translating first-order rules into vectors and then back from vectors into a first-order logic symbolic representation, there's a key aspect, which is the choice of inputs and outputs. So in a way, you can think of this as the choice of literals, first-order literals, to plug into this network for learning, which then becomes standard learning on top of that. So searching for the combinations of such literals. And also the choice of copies. And something we wanted to do, but never did, was the use of macro operators with those neural nets. So I'll come back to that briefly at the end. So the idea here is that you have some background knowledge, and now we're talking about positive and negative examples, which are ILP-style examples. And we generate a bottom clause instead of just one, a bottom clause for each example. So given the positive example, in the usual way, together with the background knowledge, mother-in-law AB if mother is C and wife CB is one such bottom clause associated with that positive example, but equally mother-in-law AB if wife AC is another bottom clause associated now with a negative example. So in this process, we're just looking at the data and trying to generate vectors or features like mother AC, wife CB. And the reason why this is called propositionalization, many of you will know, is that we're treating such variables as if they were constants, A, B, and C. And the question was, well, is this a good idea? Some people don't like the idea of using bottom clauses, but it seemed like a suitable approach for use with a neural net. So when I mentioned the macro operators, the key is that there's this choice of features, and now the features are these first-order literals. And that is key to the learning that will follow. And so I'll jump through this briefly to say that we're talking about a standard single hidden layer neural net, possibly with feedback, as in the SILP network. And we considered something called early stopping, which is, in a nutshell, the idea that you monitor performance, and as soon as your performance stops improving, or soon after that, you stop learning. And so this is the main thing I wanted to show. So this is exactly your SILP neural net that you've seen before, only they are upside down. So we've seen that if I'm given a rule, B and C implies A, then I can represent that in that way. And then I can also represent C and D implies B, and E, well, C and D and E implies B through hidden neuron 2. In fact, not D, because the weight there is negative, so exactly the same as we've seen. And then E implies D. So this is the SILP network upside down. And what we do with bottom clause propositionalization is we can translate such first-order literals into vectors. The positive examples associated with the positive label +1, and the negative examples with the negative label -1, and the input vectors have value either 0 or 1. So 0 or 1 in the input, 1 or minus 1 in the output. That was a choice. And by doing this, we want to generalize that network. Instead of having B, C, D, and E in the input, we would have such features, mother AC, wife CD, wife AC, for instance, in the input. So, given background knowledge, positive and negative examples, we can build such set of bottom clauses which are associated each with a hash table, associating the constants with those variables A, B, and C. And so we find out in this example that the features we want are mother, wife, and wife, and that for the first example, the values are 1, 1, 0 in the input with target output 1. And for the second one, it's input 0, 0, 1 with target value -1 because it derives from a negative example. So that hash function basically connects the two representations. I'll go through this very quickly. So we use a standard network training where we try to, in the usual way, reduce an error. And with the early stopping, the equation there at the bottom is what basically represents how we make that decision to stop training the neural net. So we have this standard stopping criteria, which is already derived from the K-band paper that was mentioned a number of times, and we have the early stopping criteria. So this is all about the learning. So essentially, all we are doing here is we're making a decision on the first order literals now to give to this neural net. So again, the SILP network is upside down now. Mother AC, wife CB are inputs. So we are labeling neuron L1 as mother AC. We are labeling neuron L3 instead of C, simply wife AC. And we have a way of mapping that background knowledge and examples into vectors, and therefore we have a way of training these networks with target input 1 for the first example because it's positive, -1 for the second because it's negative. Yeah?
Do I understand you correctly that you actually have two samples and one integrations of the network to learn the weights?
That's right. So the samples, so here, just in this example, we end up building just two vectors in our data set. But yes, so the first step basically creates the data set, given background knowledge and examples. The second step trains this network to learn, essentially to associate those first order literals to the target output. Thank you. And then we have a number of experimental setups. One is to use the standard stopping criteria I mentioned. The other is to use, indeed, early stopping. The other is to consider a percentage of background knowledge added, like I mentioned before, where you explicitly add some knowledge, and then you train it with the example. And then there is one variation, which is the one with simply 2 hidden neurons. And this is because of Occam's razor. So why should we start with many neurons? Shouldn't we start few and then improve and then increase the number as we go? So these are the configurations used and some of the experiments here where we compare these different network setups basically with Aleph on a number of ILP tasks. So one of the main reasons I wanted to show this is that it's nice to have a setup where we can perform direct comparisons in the ILP domain. And then, depending on how you look at this, you will consider that the drop in accuracy is too much, but sometimes not so. And the main point is on speed. So the main point is that this training, especially with earlier stopping in the neural net, really can speed things up. And there you have accuracies, statistically significant differences, and time taken by Aleph compared to the different network configurations on these standard LP tasks, Alzheimer's, UWCSC, KRK, and the ubiquitous mutagenesis datasets. Here we have results with early stopping, and that's really when we see the speed ups. And here we have some initial experiments on why should we be doing this? Why should we be using bottom clauses? And there is an interesting result that accuracy of that approach with neural nets is much higher than RST, which is a competitor, let's say, also with neural nets. So there's something about the idea of using bottom clauses with neural nets that seems to be something we should be exploring. And then you can look at all these combinations, you know, BCP, the bottom clause propositionalization with neural nets, or with some other learning algorithm like C4.5 or RSD, also with those. And we need applications in other domains to be able to conclude anything deeper from this. Again, so we can perform this kind of trick where we add those representations to the neurons and then perform learning. Again, in keeping with the tradition of neural symbolic computing, given a trained network, we would like to be able to extract representations that describe what has been learned. But this neural net is not obeying any ILP restriction. So it's not, for instance, considering any kind of chaining of the variables. It's kind of unconstrained. So one first approach was to basically go back to those hash tables and search for literals whose variables do not obey such training, and then replace such variables by disjunctions of ground terms, and show that this transformation is correct. And this was in a also in the paper. And here we have the same example with the positive and the negative examples. The substitutions in our hash table, and then whatever was derived, which is our bottom, and then chaining is not satisfied, so we replaced not that EF by not that husband one, daughter one, by inspecting the hash table. And then we can also use other ways of simplifying these descriptions, for instance, T-reduce and variations of it, which in this example produces that statement there for mother-in-law. This is fine, but I really want to mention the micro-operators, because we are having to do this because we were not clever in the setting up of the inputs and the outputs. And perhaps with macro-operators already considering that and looking at sets of literals as individual inputs, we could perhaps avoid all of that. And if we have that network set up where the inputs and the outputs are first-order literals or sets of literals, then it should be quite straightforward to, for instance, derive those decision trees that we talked about. It would be a kind of trap-pan first-order logic version. So there were experiments on whatever is extracted compared with Ripper, and looking at accuracy, how much accuracy do we lose by having to perform those post-processing, how much runtime do we lose on the speed-ups we had obtained before, which would not justify the use of the neural net, and also the size of the theory. So initial results, and as I mentioned, we need more experiments on this, show that the theories are more compact. So there is a loss. Sometimes it's quite considerable, sometimes not so, but the theories are more compact. So there's something there with this idea of a localist representation for ILP that then benefits from the use of neural nets, in particular with early stopping as part of the learning or the search algorithm to be used by these models. So yes, I think I mentioned that competitive accuracy results can be obtained efficiently with this approach. I like very much the idea that you should, in principle, be able to take any ILP dataset and use with this approach. There's no probabilistic extension of that, so this would be something to consider. Although, in my perspective, if you're using a neural net, it makes sense to leave the dealings of probabilities and uncertainties to the network to take care of. And by that I mean, for instance, the way that restricted Boltzmann machines will deal with probabilities. And then use standard logic representations at the first order level for the script. So some people don't like very much the idea of using sets of bottom clauses, but that seems to be appropriate in the context of training with neural nets. It's possible to extract relational knowledge from trained networks as long as those relations are predefined. There is still a lot of work on extracting relational descriptions from trained neural networks that are simply given. So that is a large area for research. And as I said, it can be faster, so it makes sense, I think, to consider the use of neural nets. And these are earlier results than all the very exciting results by the guys at DeepMind and elsewhere that kind of make our lives easier when it comes to trying to justify the use of neural nets in this context. So, and again, to highlight that a lot of the magic seems to happen in the choice and the number of copies that are used for these first-order literals, and potentially such macro descriptions or macro operators in the input and in the output. And if we have that predefined, then we should be able to use pretty much the standard Trepan algorithm to derive decision trees that now will have first-order rules in their nodes. And that would be a nice thing to consider and compare. And just to highlight that negation comes for free. So it's interesting that the extension of the SILP system, where background knowledge can be revised, there's no assumption that the background knowledge is correct. The background knowledge can be naturally revised by the learning. Equally, you can have negation, you can have classical, and you can have negation by failure in your background knowledge. And also here, you can deal with negation in the system, such systems. So let me move on to LTNs. I learned how to do this now. And so see, we humans, we learn from few examples. And this is one of the things that we need to fix learning from fewer examples than what's currently the standard approach. So I'll make sure there is a break at some point, before the end of those 47 slides about logic tensor networks. I gave you an introduction to the topic, which was very generic. Now I'll give you another introduction, which is more specific, and that you need to bear with me on a little bit of fuzzy logic. Can I have a show of hands if anyone is comfortable with fuzzy logic? Comfortable with fuzzy logic? A few people, okay, right. So this is where we take an approach that looks at many-valued logic, so fuzzy logic in the narrow sense, so not fuzzy logic as applied in control and other applications where you model vagueness and you fuzzify and defuzzify, but more like a first-order many-valued logic. And I have to say, I was a lot more exposed to the first variation, and I've learned a lot, and there is a lot on fuzzy logic from the narrow sense, and this book really kind of indicates that. So I'll briefly again just mention the standard stuff that we would deal with collections of objects, fix a universe, and have a characteristic function that basically defines whether an object is a member of the set or not, in a kind of crisp sense. And this would be a kind of representation of real numbers in the domain of real numbers between 0 and 10. Real numbers between 5 and 9 would have that representation. Right? So this is the standard set theory. What we do with a fuzzy set is to consider now a mapping into the real interval from 0 to 1. So what we had before becomes this for real numbers close to 7. And that's why it is a measure of vagueness. So real numbers close to 7. So that becomes our mapping. Yeah, so that would be a visual description of the difference. And these are the usual operations on sets that we now want to extend from 0, 1 to the interval 0 to 1. And they give us an indication of how to do it. So here, if we are now given these two fuzzy sets, numbers close to 7 and numbers close to 5, these are given, the union could be simply done by taking the larger of the two values. So the blue function there represents that union, right? Or the conjunction. Intersection, or disjunction, would analogously consider the minimum. So again, the blue line there in the case of fuzzy sets. Complement, so negation, 1 minus the value. So the red is the complement of the blue. And now in the usual way, we need to identify such functions in semantics for our connectives, conjunction, disjunction, implication, and negation. And these will have functional semantics. So a binary connective will be interpreted as a function f there. And they will also have this idea of an order that if x is greater than y, then x is a stronger truth than y. Everything now mapped into the real interval. And the reason why I'm mentioning this is that it's this mapping, which is already natural in the context of many-valued logics, that we will be able to use to translate those descriptions I mentioned. So part of xy implies not part of yx into vectors. It's already there. So for the conjunction, without going into a lot of detail, just to point out that there's something called triangular norm, or the T-norm, which will formalize the conjunction in that context, satisfying these properties which are listed here. So it's now continuous as that function in the usual sense. So what we end up is a whole bunch of different possibilities, and here are just 3 of them. There are many more options for T-norms. Here we are showing Lukasiewicz, Gödel, and product T-norms. So maximum, minimum, and just multiplication there as a way of providing a semantics for conjunction. Then we have the T-core norm, which is defined in terms of the T-norm. So just like you can define disjunction with respect to conjunction. Again, satisfying a number of properties. And again, with a number of possibilities there. Some of these we'll see later, well, maybe we won't, but some of these, for some of these, contrapositive holds, for others it doesn't. So there's a whole world of ways of doing this that needs to be explored in the context of machine learning. Yeah?
I'm sure about the last the product
Sorry? Yeah.
The product normal seems exactly the same as the norm.
Yeah, yeah.
Shouldn't be
maybe there is a bit of a, we can try and check that. Yeah. Yeah, thanks. Yeah, indeed. Here it's the same. Yeah. Thanks. I'll check it. Yeah. You guys can do the same as a way of getting there. The residual is the representation for implication. Again, with a number of options. Did I? Yeah, I jumped. I think this one. Just to mention the motivation for this is that the semantics of implication can be defined as the maximum truth value to be added to X in order to obtain Y. And again, described in terms of the T-norm. And it becomes this function, the double arrow there, which is defined here as the maximum Z, satisfying that constraint X T-norm Z smaller than or equal to Y. So we have a number of options again, only listing those 3 where you can define, let's say, the Gödel residual as simply the value of Y, and a number of properties that need to be satisfied by these, and of course other properties that may be satisfied by variations. The whole point is that it gives us that direct mapping into the real interval, and this is what we need. Equally, for negation, we can define not phi as phi implies bottom, as you could do in any classical logic. Here, with that setting and the residual, we can also apply such mapping for negation according to this. And here, Gödel and the product seem to coincide. So, given that very brief introduction, in LTNs, we take the elements of a first-order signature and ground them on a distributed representation. By that I mean the example I gave where John is represented by a vector where you have national insurance number, age, name, maybe a picture, and so on. So it's that vector that describes John. Vectors and tensors, we'll come to that, for learning with neural nets. And as I mentioned already a number of times, the logic is seen as a constraint on the network. And this is inspired by work on bridging logic and kernel machines, on reasoning with neural tensor networks and word-to-vec representations, and on neural-symbolic computing and the idea that we should be identifying correspondences between such symbolic and sub-symbolic representations. Really encourage those interested to have a look at GitHub, and some examples that I'll show later are implemented that in TensorFlow. So there is a TensorFlow layer, a LTN layer, which is basically the T-norms and those translations. And then there is a wrapper just for ease of specifying these things in a given application. I'll show you that in a minute. So, first order logic to represent knowledge of an agent with the signature in the usual way with everything, functions, predicate symbols, and the logic connectives, but grounded in fuzzy semantics, which is what I mentioned before. But in LTN, the non-logical symbols are interpreted as such real numbers. We called it real logic in the original, the first paper that came out without the application, and then we focused more on the actual LTN system. And that's when it was applied to semantic image interpretation last year. So grounded in the agents, sensors in the world, and that's why we had this kind of crash course on fuzzy logic in the narrow sense. So I'll very briefly going to mention first order logic signature with constants, functions, and relations or predicates with any number of arguments, and then you have some specific cases here with Cristiano Ronaldo as a football player, and relations like this player plays for this football team, and so on and so forth. So here is the kind of stuff we would expect to be able to specify, and here we have for all and existential connectives. If X plays for Y, then X is a football player and Y is a football team, and things like that. Stuff you've been seeing for a while in some of the other presentations. But then we get into the symbol grounding question. So originally introduced by Searle and Newell, and largely debated, and a very relevant problem in AI and cognitive science. And what we are saying here is that the symbol cold has to be grounded on perceptions. And this could be seen as the physical environment. And these vectors are supposed to represent such input in the real world about a number of measures, sensors, and so on. And then you can think of many different types of such sensors. And by moving into this neural representation and using such mapping already available from fuzzy logic, we are trying to address this by not having the symbol code simply out there, but by grounding it on that vector representation. And then, if it's hot, then that's also grounded in another real world situation as measured by the sensors that may be available to us. And then we can start saying, well, if it's hot, then it's not cold. So that's when we start to move up this hierarchy and start to represent such descriptions and to reason about those descriptions. And then maybe we have the concept of being warm as being something in between those two. And then maybe warm is that thing there. And it doesn't need to be, in that case, derived directly from an observation. It should be something that you can imagine from the system that was trained on cold and hot, and then it generates data for us. And that may be associated with warm. So this is a key component of some of the generative models that have been used and very successfully recently. So I think this is quite key. So to make this a bit more precise, I really want to move into some examples. So this is now, we're talking about an agent that has a set of symbols available to it describing knowledge and relationships between those. And it perceives the world via a set of sensors, and those are represented as a real number. And it may have a number of such sensors, so we need a vector in RK. And these are expressing knowledge about the current state of the world. So this signature, as I mentioned already now a number of times, should be grounded in such structure in RK. And so a natural way of performing that grounding, and that's how we do in LTN, is to map constants to a point in RK, function symbols to an n-array real function, and each n-array relational symbol to a fuzzy subset of R to the power of k times n. And using that fuzzy logic setting that I mentioned. So let's look at an example. Suppose we are here in this R2 domain, and we have some data about an object C, and this is grounded into values 2.1 and 3. And we have another object D, and this is grounded in that way, and as I said, these may be the sensors. And then we have a function, which applies to C and D, and this is also grounded in those points there, because we've defined it as just the difference. And so if now I define a predicate in this way, and the predicate can be defined in any way, and hopefully it makes some sense, we'll see some examples where it does, from a machine learning perspective, then our fuzzy set is basically assigning those values, right, in terms of membership to P. We'll come back to this in a minute. Just an example in terms of how it works in practice, the actual implementation, which uses TensorFlow. Here we are defining those constants, and then the function in this way, and then you can see the TF operator there, which helps a lot the implementation of optimizing a lot of these vectors. Now, the formulas are grounded recursively according to their structure and the fuzzy semantics that I mentioned. So a predicate will have a specific grounding, and in that case, it was here, just the difference, e to the power of that difference to some mean value. Negation would be 1 minus the grounding of phi. The conjunction here taking just one case there, the maximum, and then the disjunction taking the minimum, and then the residual, also one of those options there for implication. So now we have a way of, given this, which is data, we have a way of calculating P of C, which is membership of C to that predicate or that class. We get a value, 0.99, C is very much in the set. And P of D, D is not so much, it's towards the border. And also P of F of CD, definitely not the case, right? And so on, where I can do P of C and P of D, P of C or P of D, I can do an implication, for negation, and so on. So just the whole machinery for the fuzzy logic applied to this specific task here.
I interrupt you just for a second, because today we have some problem of connections. Okay. So you could restart. Okay, thank you.
Thanks. So the only thing missing are so how we would ground the quantifiers for all and existential, and typically we would take for all as a large conjunction, right? Yeah. Here? The minimum value? Oh, this is just an example. We just chose this to be some point in between so the average value of the data points available. Yeah? Yeah, thanks. So if we take the classical interpretation here, then we are talking about an infinite number of instances X, which is intractable. So in practice, we will take the available data. So we take a finite subset of values, and then if we want to calculate for all X, phi of X, then we take that minimum value for those data points available. And equally for the existential, then it's the maximum value because it corresponds to disjunction, right? Within that domain. So that is an interesting distinction from classical logic. So what it means is that we define an LTN variable, and it is associated with a finite domain sample. It can be as large as feasible, but what it does, and if you're a logician, you may be puzzled by this, for all x, p of x may be different from for all y, p of y. So here, the way we look at this is related to that grounding that I mentioned in reality. Or you can look at it in connection with Paul Smolensky's roles and the grounding that he performs. Variables are associated with roles. So variables are associated with a domain, and that is given by the set of examples that are available to us. So with that, so in general, for all x p of x is not equivalent to for all y p of y. It should be for all y p of y. It depends on the domain samples associated to x and y. So what we have so far is a constant mapped to a vector. Then we have a ground term where we also map that to a vector. We have a variable mapped in that way with its values, and a term f of x can be applied also in the standard way. And finally, so when we get to a relation, we have that tensor. So if we represent things in a grounded way like this, so that's where the tensor comes from. And I think it's better to look at an example again. So here we have a number of data points that we say are labeled as in class A, a number of data points which are labeled as in class B. We are told that these are disjoint. And we take this membership function using that sigmoid there. For those familiar with neural nets, you can see directly the correspondence there, right? Sigma applied to W1x plus W2y plus W3, which is what you would get from a perceptron with sigmoid activation function 1 over 1 plus e to minus x. So what we are saying is that we have the data, we make that assumption of the shape of the membership function, and we now need to learn the values for W1, 2, and 3. But we have something more. We have the data, we need to learn the values for W1, W2, and W3, but we can say that X is supposed to belong to class A, Y is supposed to belong to class B, and that for all values of X, if X is in class A, it's not in B. So the fact that these are supposed to be disjoint can be added as a constraint on top of my neural net learning. So the neural net learning would just try to learn the values for W1, 2, and 3. But now I can explicitly specify such constraints. And then I would have something like this. So the same thing we had with the fuzzy set there would be learned here. Yeah?
On the It's nice to the universal classification to the last line. So this is with these domain scenarios, the domain sample.
True.
These sample domains, are they fixed beforehand?
In this example, I think they were, and we're looking at all the values there and pairs of values. But in many practical cases, you may really not want to have to consider all those. Yeah, but in principle, the answer is yes, you would have to identify those in advance. When I give you some other examples about the grounding, so one of the examples we looked at was the smokers and friends example. There, you need to also fix the grounding in a reasonable way. So if sometimes the data points in red are supposed to be in some meaningful distance from each other, if they are going to be learned in a high-dimensional space in any, in any way that will make sense. So yes, so those assumptions, I think when I show you some of the examples, we'll have a look at that. So I mentioned there's the TensorFlow implementation. There is the LTN, which would specify things like that, P of xy or A of x for all x. And then there is now a wrapper that tries to make it a bit easier to specify these things in a more natural way. And I encourage you to take a look at the implementation. So in this ACAI 2017 paper, LTNs were applied to semantic image interpretation. And here you have the object recognition part, which basically allows us to derive such values for player, referee, ball, and whether a bounding box is part of another, whether X is left of Y, and things like that. And this was done with the convolutional neural net. At that point, you may want to add those constraints, like we've seen in that simple example. So here, if X is a number and X is part of Y, then X is a player, or maybe Y is a player. So if there's a yellow, someone holds a yellow card, that person is the referee. So in the context of that task, or zebra is a horse with stripes. So these are constraints symbolically imposed on the system which is learning directly from the data. So the way to think about this again is that we are basically defining values for these compositions of the functions and the actual constants and relations like G1 and G2 here. We're going to have a network that computes the truth value of the formulas based on such numeric values. And we're going to have constraints like P of X implies there is a Y such that RXY. And typically there is a deep neural network, and we were having some discussions around how to combine these things, whether, so for instance, in the semantic image interpretation task, the object recognition is done, and then you start learning of constraints on top of the result of that. There is a good argument for trying to do that end-to-end, where one influences the other. It's also important to see where would be a reasonable cutoff in these deep structures. Because we certainly don't want our symbolic descriptions to be talking about pixel 34 and pixel 35 and so on. So at some point in these structures, and there is a role for knowledge extraction, I think, in this area, where we try to identify at which point it starts to make sense to derive such symbolic representations. Here, yeah, I think you get it. There is a deep structure and some modularity pretty much along the lines of what I've been discussing from the beginning. And here's an example of the modularity. You know, you can look at, so you now have these vectors for V and U. These are the inputs of the neural net. These are grounded. You build your constraints when you try to learn those values for the weights, but here you also have the grounding of P of VU implies A of U. And in LTNs, you can see in the network that this is the bit that represents P of VU, and this is the bit that represents A of U, and then you combine the two to calculate the residual. Or in an earlier version, we implemented no P or A. But the point is that by doing this, the network is modular, pretty much like the ones we had seen before. So yeah, so there you have the grounding of PVU and the grounding of AU, and then the residual, the inputs of the distributed representations now. So this is the key distinction, a distributed representation with roles and a fuzzy set interpretation. So I mentioned this already. Formally, this is what we do. We are now mapping all these constraints into a number of vectors. We're trying to learn those parameters, and the task at hand is to maximize satisfiability. We want to satisfy as much as possible of the data, as much as possible of the constraints. But we know that satisfying it all, so achieving a value of 1 in our optimization, is going to be impossible. So that's why also we need the flexibility of the fuzzy sets approach. A number of references, and let's take that 5-minute break. When we come back, I'll just look at examples, practical examples of LTN, and I'll try to wrap up with some challenges in less than half an hour. So I'll try and do my best. Thank you. So these are now slides by Luciano and Michael Spranger from Sony in Tokyo, and Luciano from Trento. And what I want to do is show you a number of examples of LTN in practice applied to classification, clustering, regression. And it's very nice that, you know, it's the same framework that we've seen with capabilities to do these exciting things. But these are simple examples which are, I think, are needed in our domain, because we need to make sense, or some of us need to make sense of what these models are doing, and it makes sense to have, again, as McCarthy would say, Drosophila examples in our domain. So let's go to them. I've mentioned already the Tensorflow implementation and the link to that on GitHub. And so here's a classification task, and this is the same example we've seen before, only with more points, where we have a set of points in 0, 1 squared, and we have a classification task, which is to say that there is a predicate A, and I want to know for any point whether it belongs to A or not. So whether A of X is true for each point. And I have some positive examples, the red ones, some negative examples, the blue ones, and for the other points, I think the gray ones there, we need to decide whether they are an instance of A, so whether they belong to class A or not. So this is a typical classification task. In LTN, we would define D, P, and N, and we would simply say that for all X in P, A of X, and for all X in N, not A of X. So these are the constraints that we can add to the data we have. and then observe how the classification task is performed as, again, trying to maximize satisfiability of those constraints together with the data. But suppose now that we have a regression task. So we have a set D in the interval 0, 1, and we have a unary function. So now we have a function symbol, f. And we have a number of such pairs. And the task is to predict f of x. So now we are interested in f of x. And just like before, we set the value to be e to the power of something. Here, suppose it's just a linear regression, f of x equals y. Remember, all these things are not set in stone, right? So the constraints can be revised by the knowledge, by the data. So here we simply say for all xy, f of x equals y, and we can observe a kind of regression task where we try to learn that function symbol. If we have a multi-label classification task, again, we have a number of positive and negative examples, and we can add constraints, such as if x is labeled in a class, then it's labeled in another one as well. Or if it is in one class, then it's not in the other. Or transitivity or antisymmetry, any constraint attached to that task. So the task is to determine if they're labeled in A or not A, and it's possible that it's in neither. So in LTN, again, we would describe these things symbolically. A of x implies, AI of x implies AJ of x, for instance, or maybe the last rule there with an if and only if, where that's just double implication. You can represent that as two implications, like we've seen with the fuzzy logic interpretation. So then we can state things like that. For all x, if it's in A and in B, then it's either in C or D. And then we would observe something like this, just a visualization of the results. And there we have the green and the light green and the blue and the yellow as the classes. Unsupervised learning. So now we are supposed to do some clustering. So we don't need to have the labels given for every single data point. The task here is to minimize intra-cluster distance and maximizing inter-cluster distance. So again, these can be expressed as constraints, logical constraints on top of the data. And by the way, these should be available in that GitHub repository as kind of examples that you can actually try on the actual TensorFlow implementation. So here we can say that X is in one of the classes. Every point cannot belong to two clusters. Clusters are not empty. And you can think of different definitions of closeness and so on. There was a question about encoding graphs. And I was saying, well, you could perhaps, if your input is a graph, then you can specify that logically in terms of path and other appropriate predicates, and then see what happens. But then, of course, I'd love to hear from you guys on whether it works or not in practice. A lot of the work is in the detail. So this is also there as an example in the GitHub with some clusters being derived from those constraints and the available data. Yeah. We didn't really discuss probabilities in this context. As I mentioned very briefly, we tend to leave that, or the handling of uncertainty, to the neural net. But I'm sure there is a lot that needs to be done in terms of making sense of these explicitly in terms of probabilities. The closest we've got to that was to attach, as I mentioned, confidence values to such rules. You could associate those with probabilities, but yeah, there is work to be done on, in that direction. But I really love the way that RBMs deal with probabilities, and I think that is it's important to take that into account, that we can handle uncertainty in different ways. Probabilities is one way of doing that. If we attach probabilities to first-order theories and we start counting models, that can be computationally problematic. And here we kind of devolve that task to the neural net, and we hope to have a description that deals with that in a kind of implicit way. So, but I'm sure there is a lot to be discussed about that. And conscious of the time, relations. So this is unsupervised learning. Then again, you may want to specify whether whether there is symmetry, subset, as I said, transitive, and so on. And here is an example where, again, you have a number of red dots and a number of blue dots, and we specify relations across, as in the bottom left, or RAA or RBB. So these are constraints imposed on the available data. Another interesting application in the context of spatial relationships, you may have these relations where an object is to the left or to the right or above or below, contained, and so on. And we may want to learn such spatial relations. And again, we would be able to specify those things in logic, and then have axioms about, well, if something is to the left of something else, then that something is not to the left of the other. So similar to the part-of relation that we've seen already. So you get the idea, and then we get these kinds of unsupervised learning results, and it's interesting that we may be specifying what does it mean to be to the left or to the right, or contained. The smoking friends cancer example, which was used by MLNs, we tried to compare results there, again comparing with counting models as an alternative to what we're trying to do here, which is not to count models. And yes, so you need some kind of grounding so that it makes sense. So smokers are somehow in a related area of this multidimensional space. And that's also should also be there, and you may want to predict whether someone has cancer as a result of such other relations. Yeah, so here some examples of if X is a friend of Y, then Y is a friend of X. You may want to change that. You cannot be friends with yourself, things like that. You may want to change that as well. And finally, the MNIST with constraints. I think that's the latest example we tried, where we kind of compose images. One black on white, the other white on black. And we try to identify that these things are such composition. So in the middle example there, an 8 and number 3 in different scales. And again, you may want to say that, well, if something is a 0, then it's not a 1, and so on. But again, these are not hard constraints. These are supposed to be soft constraints on the images learned on top of the data. So Those were the examples I wanted to show. I know I have like 5 minutes to wrap up, and I wanted to give you some time for questions, but I'll stick around if you have questions afterwards. I'm happy to take them offline. We've been talking about how to think about beyond deep learning, given some limitations of such systems, despite their great success. And we proposed the general framework of neural-symbolic computing to achieve that. I just need to show this picture, which I love, and it's attributed to Marvin Minsky. The structured, the symbolic, and the neural, they're having a fight, and then ending up like that nice robot there. And yeah, the point is that if we're going to have a fight, let's try and move more quickly towards the final stage there, because we have seen it happening before, and it's time for joining forces and collaborating towards artificial general intelligence. These slides will be available. Great success, AlphaZero. Pretty impressive results, especially that it takes 8 hours, for instance, to achieve human-level performance. But then the next steps, as of December last year at NIPS, point to a number of the things we've been talking about in terms of learning the model, one-shot, zero-shot learning, abstract knowledge, explanation, and so on and so forth. There was an appraisal by Gary Marcus, which, well, I've shown the books already. There was an appraisal, which is in this paper, that looked at 10 challenges. I won't have time to go through them. And it identified 10 challenges. If you could just read that quickly as I flick through those. And two possible conclusions from that. One is that deep learning is not a universal solvent, but simply one tool among many, a screwdriver in the world in which we also need hammers and so on. And another perspective is that deep learning is universal as long as it's combined with logical interpretations. And the question is how to make it explainable, generally applicable, compositional, and to allow it to reason about what has been learned, as I started the presentation with that quote from Valiant. And just to wrap up, I would say there are three main challenges in these. They point to further research in the context of knowledge extraction from very large networks, goal-directed common sense reasoning, and also human network communication, so a network that asks questions and improves its understanding from that. There are multiple PhDs and research programs to be obtained there. Finally, really finally, just have a look at this paper. And here are suggestions for two of those multiple PhDs. Building machines that learn and think like people. And with that, you've seen this already. I'll finish here and thank you for your attention.